Well, let me start first thanking the organizing committee for inviting me to here to present our work in this nice workshop, NANOFORUM. The title of my talk is Molecular Engineering of Materials for Solar Energy Conversion. I am Naziruddin, working in École Polytechnique Fédérale Lausanne, Switzerland. As you know, Switzerland is a very beautiful country, and our institute is located very nice place next to the Lake Léman, which is the biggest lake in Europe, which stretches between Geneva to Lausanne. This is just a cover page from National Geographic, which I borrowed, and it says, we are at the beginning of end of the cheap oil. Yes, indeed, we are at the beginning of end of the cheap oil, and what is the solution for our planet? The nuclear power is a possible solution, but it is not a permanent solution because of the pollution and also the nuclear radiation, which is not going to be safe for generations to come. And the one possible solution is solar energy conversion. Of course, there are many technologies to convert solar energy into electricity, but the technology which we developed at Lausanne is very interesting because it uses very cheap material and non-toxic and easy to fabricate. And here I'm just showing you one panel which Japanese companies is producing for rooftop applications, and this is a solar cell used on Dyson solar cell based on our technology. And if you dig into the whole technology, and if you take a cross section of our technology, it's so simple that we are having only two conducting glass electrodes. One is a working glass, which is here working electrode, which is conducting glass, and then on top we put between 2 to 10 micrometers thick of titanium dioxide layer, and then on the titanium dioxide we coat mono layer of dye onto the surface of the titanium dioxide, and we introduce a redox couple in between the working electrode and then the counter electrode. Counter electrode is again, it's a conducting glass coated with a small particles of platinum. And if you go to the working mechanism of our Dyson solar cells, and the dye is attached to the TiO2 surface, and once if you excite by photon, the dye goes to the excited state. In the excited state, this dye has two configurations, one singlet and then the triplet. And the singlet excited state as well as the triplet excited state, both states have sufficient driving force to inject electrons onto the conduction band. Now, what happens to the fate of the oxidized dye? It comes back and then takes the electron from the redox couple, which is in the solution. And then the electron which is in the circuit goes to the counter electrode, and then the electron which is in the counter electrode comes to the redox couple. That way, the whole circuit is complete. The cell is regenerative and non-destructive. Now, the total power conversion efficiency of this cell is the amount of electrons we are injecting, that's the number of photons, number of electrons, and the difference between the conduction band and then the redox couple, that's the open circuit potential, and fill factor. So the product of current, voltage, fill factor gives us, divided by the energy, divided by the light intensity, gives us the power conversion efficiency. And if you go into further, if you zoom out the further electron kinetics of this electron transfer processes, the excited state electron injects onto the conduction band in femtosecond domain, typically below 50 femtoseconds. And then the singlet converting into the triplet is again in the range of 50 femtoseconds. And the triplet excited states also inject electrons in the picosecond domain. And then the electron which is in the conduction band can also come back to this is the side reactions. These are the two side reactions where the conduction band electron can come back to the oxidized redox couple, or it can come back to the oxidized sensitizer. So these two side reactions one has to prevent by manipulating, engineering the sensitizer at a molecular level. That's what you are going to see in my talk. So here is the typical sensitizer, which has two metal to ligand charge transitions. So we are using ruthenium complex. Ruthenium complexes are very good for this type of applications because they are highly stable. You can take out electrons 2 or 3, or you can put the electrons back in 2 or 3. The sensitizer is very stable, very rugged. And then you have these carboxy groups which are anchored to anchor the TiO2 surface, and these are the two NCS groups. They have some special functionality to tune the metal redox properties, as well as once if you inject electron from metal to the ligand, from ligand to the conduction band, the generated hole, positive charge, is shared by the NCS, and this NCS is shared by the iodide. So that way the regeneration of the dye is much faster. So there is a purpose to have a NCS group in this complex. And this type of complexes typically show in the visible region, absorption maxima. And here I'm showing the power conversion efficiency of this type of sensitizers. Here I'm comparing with these 4 carboxy groups. They have 4 protons. And if the dye goes with 4 protons onto the TiO2 surface, what happens is the conduction band lowers, and then the difference between the conduction band and then the redox couple is smaller, and thereby we get less open circuit potential. As I mentioned in the previous slide, the power conversion efficiency is a product of current and then the open circuit potential. And here we are getting a huge current having the 4 protons, 19 milliamps per square centimeter. But at the same time, we are getting only 600 millivolts open circuit potential. Thereby, the power conversion efficiency is only 7.4. Now, take another extreme case where I'm removing all the protons from the sensitizer, and I absorb this sensitizer onto the surface. Now, the current generated by this sensitizer is only 13 milliamps. But on the contrary, the voltage is 900 millivolts. Why we are having high voltage? Because when we absorb the dye by deprotonation, the deprotonated dye puts some electron density onto the TiO2 surface, thereby it increases the conduction band. The distance between the conduction band and the redox couple is increased, and thereby we get higher VOC open circuit potential. Again, having higher open circuit potential is not good, so you need an optimum open circuit potential and optimum current to get the optimum power conversion efficiency. And to have this, you have to engineer at a molecular level to get a 1 proton, and using this 1 proton, you can get almost 10% efficiency. And how do you get 1 proton? You have to manipulate by a small molecule which has a higher pKa than these carboxy groups. You deprotonate this one, and then you add this deprotonated small molecule into this solution to give you the measured number of protons, to give you the highest possible photon to electron conversion efficiency. And this type of dyes having manipulated with 1 proton gives you 11.2% efficiency. This is the highest efficiency we have obtained using dye-sensitive solar cells. Now, so as I mentioned, there are 2 side reactions, which are the electron in the conduction band can come back to the oxidized redox couple, that's a triiodide, or the electron in the conduction band can come back to the oxidized dye. This is a recombination. These 2 side reactions one has to prevent by manipulating the dye structure. So in the previous case, we have used 2 carboxy bipyridine ligands, and when we absorb the dye, you don't need 4 carboxy groups to attach right onto the TiO2 surface. 2 carboxy groups are sufficient. And then what we have done is we removed one of the BP ligand and incorporated alkyl substituted bipyridine ligand. What happens is this type of sensitizers adsorbed onto the TiO2 surface, it forms some kind of a network, thereby preventing the triiodide reaching onto the surface. You can effectively block the electron coming back to the triiodide surface. Not only that, having this type of long chain molecules, it provides you an added advantage since they are hydrophobic, and the sensitizer can be prevented by water-based desorption. Thereby, you can, the cell efficiency and the cell stability enhances significantly. And the second side reaction, what we have prevented by incorporating a donor unit. Here, the oxidation potential of metal is 800 millivolts versus SCA, and then here the oxidation potential is slightly lower than the ruthenium. Once the electron is injected through this carboxy BP onto the conduction band, the generated hole positive charge is sucked by this donor group. Thereby, by increasing the distance between the electron and then the hole by simply 4 Armstrongs, you can decrease the recombination by 1,000 folds. So this way, one can really manipulate at a molecular level to have your desired reactions. All these dyes, which we have discussed, has a low molar extinction coefficient. This is another interesting property which gives us higher power conversion efficiency if we have a higher molar extinction coefficient. In order to increase the molar extinction coefficient, we have manipulated the dyes by extending the pi system. This is a simple carboxy bipyridine ligand, and then we incorporated a vinyl group between the carboxy and then the pyridine ring, and here we have a vinyl and then the phenyl group, and here we have replaced one of these groups with the aliphatic chain, incorporating all our previous requirements. As you can see, going from a standard molecule, which has a 535 absorption maxima, and we moved to the absorption spectral properties 575 by molecularly engineering the sensitizers by incorporating various groups. Here is just a direct comparison of absorption spectra of a standard molecule. This is a standard molecule, and this is a newly modified molecule, which gives you around 20 nanometers redshift of the spectral responses. All these spectral responses are very important because if you see solar emission coming onto the Earth's surface, half of the light is up to 700 nanometers, and the remaining half is above 700 nanometers. So if we can manipulate these sensitizers, which can absorb above 700 nanometers, then we can enhance the total power conversion efficiency beyond 12%. So here is the IPC. This is a typical curve what we generate from the solar, these photovoltaic measurements. This is photon to electron conversion efficiency. If you remember the previous IPC curves, at 700 nanometers, we never had more than 30%. And with this modified molecule, at 700 nanometers, we still get very close to 70% injection efficiency. So this shows how one can really manipulate the sensitizers to your advantage. So still we have to improve the spectral responses. If you see the solar emission spectrum, which goes up to beyond 1000 nanometers, and our sensitizers, they absorb below 700 nanometers. In order to do that one, here we have taken out two NCS groups. The purpose of these NCS groups, I have discussed before, that these groups, they really manipulate their metal oxidation potential, and we have replaced these two nitrogen NCS groups by this phenyl carbanion group, which has a similar properties to tune the metals, the spectral responses. On the other hand, if you see the fluoride groups, these fluoride groups, they have a functionality like the sulfur group, and the interaction between the triiodide and then the sulfur, and the same we have imitated here by incorporating the fluoride. And once the electron is injected from the ruthenium to the conduction band, the positive charge is shared by this carbanion and followed by fluoride, and the fluoride is having some kind of interhalogen compound with triiodide, giving you highest efficiency possible. And without further optimization, we did achieve, using this molecule, very close to 10% efficiency. Here, before I go to that efficiency, I show you how the HOMO-LUMO levels are tuned here. This is a standard molecule. The LUMO levels are carboxy BP ligand, and then the HOMO levels are the NCS ligand. And in the newly designed molecule, the LUMOs are again carboxy BP, but the HOMOs are metal-centered as well as the carbanion. So this is the total power conversion efficiency of using the new dye. This is without optimization, we have obtained 10%, and there is a still possibility to enhance this efficiency further. My time is up, but I will just very quickly scan some of the concept which we are working. Very fast I go, and just to show what the research activity we are having. If I have a 2, 3. Oh, well then, okay. Well, this is the dye which we have achieved, and here I just want to emphasize the advantage of, if you agree, otherwise I can stop. Yeah, so the advantage of this dye is, if you go back to all our ruthenium sensitizers so far, all they are having NCS groups. All they, invariably, all they have NCS group. And this is first time we have achieved without NCS group a dye which gives 10% efficiency. And this is the beginning, and we can enhance further this efficiency. Another added advantage is having NCS is a bidentate ligand, ambidentate ligand. It can coordinate through the nitrogen, or it can also coordinate to the sulfur, and the separation of these two isomers are really a problem. But here we will get only one isomer, and then the synthesis is easy. Very quickly, I just show some of the metal complexes. The ruthenium is expensive, but in order to go further, to have a very less expensive material, we developed organic sensitizers. And here I have shown 4 organic sensitizers, just concentrated on these 2 cases. That's a D5L6 and the D21L6. So in these cases, we have a donor fraction, which is triphenyl substituted amine group, and then the bridge, which is thiophene, what we call conducting bridge, and this is the anchoring group. In all these molecules, we have a donor, and then the conducting bridge, and then we have an anchoring group. By using this type of molecules, we do get very close to 7.25% efficiency. But here what I want to show you is, emphasize is, how one can really manipulate the molecular level. Say this has no methoxy substituted group, and this one has a methoxy substituted dye. You can see the red response of this molecule, and not only the red response of this sensitizer, but if you go to the stability test under heat and light soaking conditions, having methoxy group gives you very close to 90% stability under heat and light testing conditions, and whereas without any substitution, the stability goes down significantly. Here I am showing you another class of compounds where we have replaced the triphenylamine group by extended the donor system to enhance the optical response beyond 430 nanometers. Here it's 452 nanometers. And this type of dyes gives you efficiencies very close to 8%. And then the spectral responses you can tune by incorporating the number of thiophene bridging units. Yeah, here is another interesting dye. So far, all the other organic dyes which we have tuned, they absorb below 500 nanometers. And if you want to cover the whole visible range, you need sensitizers, couple of them, so that you can cover the whole visible region. And here we have selected one dye, which is a squirene, which has a very interesting near-IR absorption. And this type of dyes are very useful for building integration because they can generate electricity. At the same time, they can be prevented heat by near-IR absorption of the radiation. You can have a window in this region where the light can penetrate very easily into the room. And using this type of sensitizers, we did obtain 5.5% efficiency, but if you see these spectral responses, this absorbs in the near-IR region, and then the previous sensitizers, they absorb in the visible region. By combining these two, one can obtain significant enhancement in the power conversion efficiency. Here I am just showing comparison of spectral responses of free dye of the JK2, that's a visible absorption dye, and red one is the near IR absorbing dye, and then the black one is the combined these two dyes onto the TiO2 surface. And if you see the power conversion efficiency of this dye, the blue curve is pure organic dye, which absorbs below 500 nanometers, and the red one is the one which absorbs in the near IR region, and then the black one is the combined efficiency of the blue and then the red one. So the power conversion efficiency is around 15% higher than the individual dyes. Here I'm giving one more example. Phthalocyanine is a very interesting class of compounds. They are highly stable, and the people, the manufacturer, they give you 100-year stability. These molecules, you can burn them, you can sublime them, they are very stable, rugged. But the problem with this type of dyes are, they need a directionality. And people, they have used this type of molecules for solar cell applications, but the problem with this type of molecule is they are highly symmetric, they don't have a directionality in the excited state, and then the dye efficiency is less than typically 15%. Now, if we replace one of the three of these carboxy groups with alkyl tertiary butyl groups, and these tertiary butyl groups enhances the solubility, and it gives you a directionality in the excited state. When the photon comes, and the electron knows where to go, and it goes to the TiO2 carboxy substituted ring, and then it gives you a highest possible efficiency. And this is another dye which is a parylene, and the solvent has a significant influence on the power conversion efficiency. Here, if the ethanol, you get only 2%, and this is a protonated and polar solvent, the efficiency is below 2%. And if you go non-proton, non-protic, non-polar solvents, then the efficiency is 7%. And this shows how one has to really molecularly engineer solvent and sensitizers to give the highest possible efficiency. And with that, I just show you some of the publicity based on our companies. So this is the one company which is producing very nice panels to integrate into the into the building architecture. And this is Indian lady which we're using for our solar cells for charging mobile phones. And this is a Japanese company producing stools to put in your gardens. In the daytime, you can convert the solar energy into electricity, store it, and provide in the nighttime for for the electricity, lighting. And another is Professor Uchida. He is an electrical engineer. He has manufactured his own car based on our solar cells, and he has participated in Tokyo car race, and he won that one. And the future is one day So this is in Narita airport, and one of our company has put the model plane where based on our Dyson solar cell. And you can see once if you put the lights on, the flight starts and doesn't move, but it's fixed. Yes. With that, I thank my coworkers who are there, and thank you for your attention.